Hello and welcome to this clip taking you through the second homework on manganate redox titration questions. You've seen the mark scheme to it if you can set the same homework, and this is really just to expand a little bit on the mark scheme. So in this first question, which has been particularly requested, it says that vanadium can exist in a number of different oxidation states. One compound of the vanadium is ammonium vanadate 5, and this contains the ion VO3-. It says it can be reduced to V2+ in several steps using zinc metal and an aqueous sulfuric acid. So you can obviously see it's given you data, and what this means is that although the original starting ammonium vanadate 5 has a volume of 25.0 centimeters cubed and a concentration of 0.1 moles per decimeter cubed, the fact it says it's completely reduced to V2+ means you can assume that also you have the same values for V2+. And then the question goes on to tell you that the resulting solution, so the resulting solution means V2+, is titrated with 0.0500 moles per decimeter to the -3 of manganate, and 30 centimeters cubed is required to oxidize the V2+ back to VO3. So from start to finish, that's your complete process. But it's the second stage that is your redox titration of interest. And we have data for both the oxidizing agent and the reducing agent. So let's now do the calculation. So it says, show that the vanadium has changed oxidation state from +2 to +5 in this titration. So in other words, what they want you to do is to use the titration data to support this statement. So let's have a look at what the titration data tells us. So first of all, it tells us the number of moles of V2+ and MnO4-. So what we've got to now do is use the oxidation number changes to support the change in oxidation state. So the manganese in MnO4- has changed from +7 to +2 in Mn2+, so it's a decrease by 5. At the same time, the vanadium, like the question tells us, has increased by 3. So the oxidation state change ratio, say that again, the oxidation state change of vanadium to the oxidation state change of manganese is 3 to 5. So the mole ratio of vanadium 2+ to manganate is 0.0025 to 0.00150. If we divide each of those by the smallest to clean the ratio up, that gives us 1.67 to 1, which is a similar ratio to the oxidation state change ratios. So this was a slightly tricky question, but what they want you to do was to relate the oxidation state change that was obvious to the mole ratio change. So the connection between the two might have not seemed immediately obvious, but once you've had a look at it mathematically, hopefully you can see it's fairly simple. So moving the page down a bit, it says suggest an equation for the oxidation of V2+ to VO3- by MnO4- under acid conditions. So acid conditions means in the presence of H+, obviously. So what we need to do here is to draw out the two half equations. So what we've now got to do is to work out how many times each side has to be multiplied to make the electrons the same. So you can see that you can cancel the electrons. So let's do that first of all. Now you can also cancel other things as well. You can cancel the H2O's. You can also cancel the H+'s, like so. So that gives us a final equation to put down in the answer line. Okay, so let's go on to the next question. So it says the percentage by mass of iron in the sample molecular can be determined by titration against acidified potassium manganate 7. So it gives you 4 stages, and I think the most important thing to keep an eye on here is the fact that you've got copper acting as a reducing agent. So in stage 4, you have aqueous potassium manganate, which is an oxidizing agent. So copper and manganate will obviously react together. Which is why in the first part of the question it asks you to think about why it's important to remove all the copper. So on the one hand that might happen. On the other hand, during the titration itself, if you had any copper impurities in there, they might react with the Fe3+ that's being formed during the titration and reduce it back into Fe2+. So in other words, send the equilibrium back the other way. So looking at the next part of the question, it should be fairly straightforward if you assign oxidation states. So once you've done that, you can see what's being reduced from what. So first you state what's reduced from what oxidation state and in what species, to what oxidation state it goes into in which species. So Mn is reduced from +7 in MnO4- to +2 in Mn2+. At the same time, iron is oxidized from +2 in Fe2+ to +3 in Fe3+. So in this next question, you start with what you can work out the moles for. Obviously, it's going to be MnO4. So applying moles equals volume times concentration, that gives you 4.5 times 10 to the minus 4. So the mole ratio of iron 2+ to MnO4- is 5 to 1. So we multiply 4.5 times 10 to the minus 4 times 5 to get 2.25 times 10 to the minus 3. Now we can work out the mass of iron that we've got. So you multiply your moles times Mr to get 0.1256 grams of iron. So that gives us 18.6% as our final mark. Now for this next bit, ideally you'll have your script in front of you, because the next page asks us about these 4 stages. So you'll need to, before the clip continues, just pause the clip and have this in front of you whilst we do the next part of the paper. If you don't have the script in front of you, you might want to pause the clip anyway and just copy down these 4 stages, so then you'll know what we're referring to in the next screen, which will not have this part of the question in it. So the first part of the next part of the question doesn't require you to have access to that information, so we can do that straight from what's on the screen here. But it does require us to know the half equation for the oxidation of iron. So the manganese dioxide equation stays the way it is, and the iron equation gets multiplied by 2 to make the electrons balance, like so. So this next part, it does actually ask you to use information from the previous stage, so you need to have that copied information or the original script in front of you, so you can refer back and forth between the screen and your script. So again, going for the data that tells me what I can work out the moles of, it's going to be Fe2+. So the number of moles of Fe2+ used is your 100 over 1000 to convert it into decimeters cubed, and then times that by 0.200. So again, N equals V times C from first year chemistry. So you get the moles of reacted iron by difference between the original amount of Fe2+ and the unreacted amount. So the next thing to do is to get the mole ratio of iron to manganese. And from the equation at the top, you can see quite clearly that it's a 1:2 ratio. So dividing the manganese moles, the iron moles by 2, that's 0.0077 divided by 2, it gives you 0.00385 moles of manganese oxide. We're using moles times Mr to convert to mass, it gives you 0.335 grams of MnO2. So dividing the mass of MnO2 from the titration divided by the mass of the impure MnO2 sample, you get 0.335 over 0.504. Multiplying that by 100 gives you 66.5%. So the next part is a similar style of question. It gives you the stages of your titration procedure, the data that you need as you go, and the first part asks you to construct the equation, the balanced equation for the redox reaction. So again, we need to remember do the recall of the Fe2 plus to Fe3 plus equation. It's dead easy. And now what we do is we try to multiply how many times that needs to happen. So we have 6 electrons in the dichromate half equation. So this one is times 6, and the dichromate half equation is times 1. So all you do is you add them together, but making sure that anything that has iron in it is multiplied 6 times. So coming on to the final part of this pack of questions. So unfortunately I thought I had that final page uploaded, but I hadn't on my PDF, so I've just popped it in here for us to follow. So the thing you do is you work out the moles of whatever you can, which in this case is Cr2072-. Not forgetting the mole ratio, we can now work out the moles of iron 2+. So that gives us 2.12 times 10 to the minus 3 moles. Now we convert to mass by using moles times mR. It must be in the form of FeSO4.7H2O, because that's what they want us to actually calculate. It's not just the iron, it's the iron in FeSO4.7H2O. So obviously there's only 1 mole of iron per mole of FeSO4.7H2O, so we can transfer over the value for the moles of Fe2+ as the moles of FeSO4.7H2O as well. So that gives us 0.589 grams. Now to work out the percentage purity, we've got to divide that by the original sample, which was 0.655. So that gives us 89.9% purity. Okay, so that's the end of the set of manganate questions that I set people for homework. Hopefully you found it a useful clip, a useful walkthrough on how to do these. The main thing would be to think about what seems to be popping up all the time. It's going for the moles of the substance for which you've got the volume and also the concentration. So N equals V times C starts you off. Then you use the mole ratio. So it's data, moles, equation, moles, answer essentially from your first year chemistry. So once again, thanks for listening. Hope it was useful, and maybe see you soon.